3, 2, 1, and live. All right, awesome. Thank you so much. Sessions after lunch are always hard for the speaker and for the attendees as well. My name is Arun Gupta. I work for Amazon. I work as a principal technologist in their open source team. I'm also the governing board member for Cloud Native Computing Foundation. So my role is to basically define the strategy on how different service teams work with CNCF, and I'm going to bring that feedback back in from a lot of our customers. I do talk to a lot of customers, primarily focused around the container services org. Not going to get into what all we offer, but what we have is Amazon EKS, which is our managed Kubernetes service. I'll talk briefly about that. But this talk is particularly around machine learning using Amazon EKS or Kubernetes, because one of the core tenets of Amazon EKS is upstream compatibility. So if it works in upstream Kubernetes, it will work on Amazon EKS as well. Generally, customers think about why is Kubernetes being used so widely around for machine learning workloads. It has the composability, it has a scalability, it has auto scaling, it has load balancing, usual things that you would typically expect from a machine learning workload as well. So this is exactly how we have been working with our customers for the last several months who have been running, say, machine learning workloads on top of Kubernetes. So let's talk about sort of what is our machine learning 101. You can realize it in a variety of ways, but at a very top level, essentially what you have is, you want to build a model for something, which is like a machine can understand. And in order to build the model, you got to train the model. So training is basically your blue code in the middle, which is sort of the application logic that you write, using Python, Scala, or Java, whatever your favorite language is. And that training module is fed some training data. So for example, you could be, I'm going to show you a glass, and in the glass there's going to be liquid, and you're going to tell me whether it's wine or beer or it's water. And that's the model that you want to build. And the whole idea is that once I build that model, then if I feed you any image from real world outside the training data, you'll be able to tell me what it is exactly. Okay? So what you do is you feed that training data, you have a whole bunch of images that you feed to the training module that then generates a model. And then you have a separate set of test data, for example, that, okay, outside the training data, which is going to test the accuracy of the model. That, okay, you built a model, here is my test data, does it make sense or not? And the optimization of the training module is super important as well, because training could take days and hours to run. So you got to understand that how optimized your algorithm is. So you'll choose the right algorithm based upon what your use case is. Once the model is ready, then you get into what we call as the inference phase, which is sort of where you say, okay, now give me data from real world. I'm going to give you any image, so your model is ready, and then I'm going to make predictions that, okay, it's a cat or a dog. It's a hot dog, not a hot dog. So you can make those kind of fun predictions. End of the day, it all boils down to the fact that how good are your predictions. So you look at sort of the accuracy of the model when you're building the model, that it is at 90% accurate, and then you're looking at the optimization of the module of the model, that how quickly you're able to generate the model, how many training runs you're doing, and then finally how good are your predictions. So if you take a look at what is sort of how we look at machine learning, Amazon has been doing machine learning for over 20 years. When you order, how many of you are Amazon customers, Amazon.com customers? Thank you. We are customer obsessed. So am I. I've been a customer for over, I think, almost 12 years. Anytime you order something on Amazon.com, it goes behind the scene, it figures out, it's going to pick the packet, it's going to optimize the route through the warehouse and bring it to the front so that it can be shipped to you. That's using machine learning algorithms from the very beginning itself. So there are lots of places where ML is being used across Amazon, across the board. But the way we look at it is, there is the bottom layer, which is ML frameworks and infrastructure. This is meant for expert machine learning practitioners who knows exactly that I need a GPU. I need a TensorFlow framework. I need Gluon. I need Keras. I need PyTorch. What is the framework that you need? You are willing to build your own model, and you are willing to train your model and put that into production. And then you're able to manage your entire infrastructure. Then comes sort of the middle layer, what we call as the ML services, which is our fully managed service, which is meant to sort of commoditize, and everybody can take a look at it, that I want to run with, I don't have the resources and the time to build a model or train a model. I don't know which algorithm to choose. I cannot manage that infrastructure. Go to SageMaker. All of those tools are available to you as a fully managed service. That's where customers like Intuit are running it. And they have this thing called as Expense Finder, where they look at sort of your entire year worth of expenses. And they can give you, hey, by the way, these $4,300, that's the average thing that they save for their customers, that these $4,300 you can deduct as business expenses. And that's how they're using SageMaker, for example, for customers. And then last but not the least, what we have is what we call as AI services. These are also called as cognitive services. We have vision, speech, language, conversation, different capabilities, because these are more human cognitive services. And you don't need to know anything about machine learning for these at all. So this is sort of, for example, if you take a look at, say, a recognition video. So essentially what you're doing is you drop a video to this recognition video service and say, on this street view, tell me every time a Lexus hybrid crosses. And you just provide sort of the input data for it. It runs behind the service for you, and then it will generate that data for you automatically. Or you can take a look at Lex, which is sort of the back end for Alexa or Echo. So you say, and it's doing all the natural language processing and everything for you and generating that model and then giving you real-time conversations. Now, at a very high level, this is sort of how we see the capabilities in Amazon ML stack, but it's not just about providing that ML stack. You need that storage and analytics capability for the platform as well. You need that high throughput, low latency, performance file systems. You want that real-time analytics to be running to be able to feed back into your inference model. So if you take a look at storage, we got, in terms of storage, pick a relational database of your choice, pick a time series database, pick what you want, graph, document database, key value, in-memory cache, whatever you want to see in terms of storage, we got that capability. Similarly, on the analysis side, you could run all sorts of real-time analytics using whether it's Kafka, whether it's Kinesis, whether it's running SQL queries on S3, all sorts of range. So the capability, this is when you're evaluating your machine learning platform, this is what you should be looking at it. Now, where does Kubernetes fit into this picture? Kubernetes fits right in the bottom layer. This is where meant for expert machine learning practitioners. When customers choose Kubernetes, they're ready to embark on that journey where they will be able to play around with it. They have lots of levers and knobs that they can tweak around in order to make the system work for them. So our talk is going to primarily be focused on this bottom layer, and that's where we will talk about, okay? So why machine learning on Kubernetes? So there are three primary reasons customers choose Kubernetes for machine learning. So composability, portability, and scalability. Composability is important because when you are building machine learning, there are lots of different stages for machine learning. You need to identify your data. You need to tag your data. You need to classify your data. You need to clean up your data. You need to have an ingestion phase. Then you are doing the model training. Then you're doing the inference phase. Then you have to scale that infrastructure. All of these are essentially different microservices. And guess what? Kubernetes is really good at composability. And that's where each of these services could be built by different teams, and then they can compose together as one big machine learning process for you. Portability is super important because when developers are building these machine learning models, they're ideally building it on their laptop. But now they want to scale up to their on-prem environment or to the cloud. And that's exactly what Kubernetes provides very easily, where you can easily migrate across different computing environments. And scalability is the last part because essentially now you're running today on a single node, but then you want to quickly expand into a multi-node, multi-pod environment, for example. So this is exactly what Kubernetes provides you. And once you have understood the basic concepts of Kubernetes, those same concepts can be applied, whether it's a stateless application, which is where Kubernetes is used quite heavily, but also for stateful applications, which is what machine learning happens to be. And we'll get into that part of it. So this talk is primarily focused on how we are helping customers run their machine learning workloads on Amazon EKS. But what is Amazon EKS? Amazon EKS is a managed Kubernetes control plane. Now, if you think in terms of Kubernetes, it comes with two key pieces. One is a control plane, which is sort of the layer on the top, which is where you use kubectl to talk to the control plane. And then the control plane then talks to the data plane, which is what is running in the cloud. Both are running in the cloud, but which is in the data plane is the EC2 instances where your containers actually run. So with EKS, what you get is a managed control plane. Now that's how we started. And the managed data plane would be coming later this year. The important part to understand is the core tenet of Amazon EKS is 100% upstream compatibility. So whatever you're doing in upstream Kubernetes is exactly the experience that we're going to give you as part of Amazon EKS. And so you could be leveraging that on your desktop or on your on-prem or wherever you are, but on any other cloud, but that's the same experience you're going to get. There is no forking, no patching, no internal versions maintained for the Kubernetes code source. Just like any other AWS services, all the ilities, as I say, reliability, scalability, high availability that you expect from an AWS service, that's exactly what we have. And as a matter of fact, Amazon EKS is one of the fastest growing service for AWS, and the kind of customers that we're getting is just mind-blowing. We also have integration with different additional AWS services. So for example, you want to have your Kubernetes control plane logs being sent to CloudWatch. Sure, it's there. You want to have an integration with IAM because that's what AWS customers use. That integration is there. You want to make sure that all your kube control commands are sent to CloudTrail. That's all there. So all of those integrations with existing AWS services are undifferentiated heavy lifting if you're running a self-managed Kubernetes cluster on EC2. But those are all available as part of Amazon EKS. So how do you start with EKS? It's very straightforward. eksctl, or just like kube control, there is an EKS control. You download that CLI, literally just brew install the CLI, and it'll create all the resources you need for the cluster, okay? So I want to give a shout out here to Weaveworks, because Weaveworks is a very good partner of AWS, and they are the ones who actually build this CLI essentially. So how do you get started? You just say brew install Weaveworks from the Weaveworks tab. You install EKS control, and one single command, EKS control create cluster. That's it. That'll create your cluster. So it'll create the control plane for you. It'll get the data plane for you, and it has a reasonable number of defaults. You don't have to specify a name, but it'll generate a cryptic name for you. By default, it uses M5 large nodes. Those can be overridden. It uses US West 2 region. It uses a dedicated VPC. So there are reasonable defaults. The command is fairly straightforward to generate the cluster.
Can you tell us, when you do the brew install, does that automatically install all the other stuff you need?
Well, so the question is, when you do brew install, does it install every other stuff that you need? Brew install Weaveworks tab EKS control will install EKS control. You still need to install kube control by yourself, and that's how you communicate with the cluster. Now, oftentimes, when you're running a machine learning workload, you would not run it on a CPU-based workloads. You would run it on GPU-based workloads because, end of the day, if you think about machine learning, everything that you're doing is matrix multiplication. Everything is converted into a vector, and then you're multiplying matrices. And then when you're doing that multiplication, you want to make sure that is parallelized. And that's exactly where GPU starts shining up. The kind of capabilities that GPU has, the number of cores that it has available is far, far much more powerful than CPU. Higher cost, but higher cost, that means you get the job done much faster. So, sorry, the point that I wanted to highlight here is, in this one, I'm saying eksctl create cluster. I just specify the node type. The moment I say p2.xlarge, which is a GPU type that is available on EC2, this is now going to create a GPU-powered cluster. So there's a convention over configuration. By default, it takes 2x M5 large, but now you're overriding it.
Yeah. Do you have support for node pools?
You mean node groups?
Well, in Kubernetes, it has node pools. So in other words, you can have, you spin one up with lower, and then you create a node pool that's just for GPUs.
So yes, the question is, do you support for node pools? So you can create in one, and I'll talk about what the design patterns are, how you can have multiple node groups with different processing powers. We'll talk about that. We'll get into that. to your question. How do you set up your Kubernetes for machine learning? So let's take a look at option number 1 first of all. Well, so what you do is you create a EKS cluster. Control plane is same, doesn't matter whether you're using for machine learning or not machine learning. But in this case, what I'm doing is I'm creating a EKS cluster. In the EKS cluster, I have 3 P3 instances, and P3 is a much powerful instance, but it's a GPU powered instance. And the P3 instance is set up in an auto scaling group so that your jobs are not sitting idle or your P3 instances are being utilized. If they're being underutilized, it'll scale up and down based upon the metrics. So that's one training cluster. Then you'll create another cluster, which is an inference cluster. So you're keeping your training cluster and your inference cluster separate, because typically the people who are building your model, there's a data scientist, you give them an independent cluster, they're generating the model over there, and the people who are building the inference, that means who are leveraging that model and putting into production are the developers. So you can keep these two clusters completely separate, separation of concerns. So what happens is now your data model is sitting in S3, which is sort of your training data, which is what you're going to feed to the model. You do number of training runs, and once you have the accuracy typically around 90%, maybe higher, then you have the train model, which is again sitting sort of in an S3 bucket. Then you feed that to inference, and eventually your customer actually is able to see that into production. So end of the day, this is sort of your typical cycle, okay? This pattern, what we call as a dedicated Kubernetes cluster, because essentially you have one cluster with one node group and another cluster with another node group of different instance types, but no sharing of responsibilities here. How do you get started with that? In this case, all I'm doing is I'm saying EKS control create cluster. I specify a cluster name, the number of nodes, and I'm saying P38XL, okay? And I can similarly create another inference cluster in this case, and in this case, I'm just using the P2.extra-large. So you can look at the EC2 instance types, and it'll tell you the number of GPUs that are on each of the instance types, and that's how you basically estimate what your cluster is going to look like. Let's look at the second pattern. To your point, in a same cluster, I can have 2 different node groups now, okay? I have 2 different node groups, one for training and one for inference. And the way I do that is, of course, I set them up as 2 separate node groups, but each node in the node group has the right label to it as well. So in this case, for example, on the left, you can see there's a role::train, and on the right, you can see role::inference. The overall model stays pretty much the same. You take the data from S3 bucket, feed it, generate the train model, feed it back, do the inference, and then that's the end result that the customer sees. But the way now you deploy the data, or the way you deploy the job, because end of the day, these are pods running that are going to do the training for you. Now you're going to use node affinity in this case. All you're saying is, hey, pick the node selector role::train, and this is going to go to the training node group here. This is a unified Kubernetes cluster. So again, very easily, simply possible using just the EKS control. In this case, we're using a configuration file. So all I'm doing is here, I'm saying this is a GPU, CPU cluster, specify the region here, specify the node group name. So these are 2 node groups in one cluster. Specify the instance types. This is where I'm assigning the labels over here. These are the instance types, and I define the capacity here. So all I do is just say EKS control. Instead of create cluster, take this configuration file and have my everything documented in it. A lot of our customers use CloudFormation, Terraform, all sorts of ways to create these clusters, but this is sort of the simplest way by which you can easily get started. And then from this, you can also generate your CloudFormation template, which you can then start tweaking on what I want to do with this. A slightly extended pattern that we have also seen with a lot of customers is where they will have not just training and inference, but also the application sitting in the same cluster itself. Now imagine in this case, your training and inference is constantly happening. That is not even visible. It's the same set of folks working on the training and the inference part of it and the application. Now, your application may be feeding back training data into the training module, which is then running a model. Optimized model is now available for inference, and then your app experience is evolving every day. So for example, not specific to here, but think about the Netflix use case. every day that you use, the movie recommendations that you pick, based upon that, your Lolomo or the list of movies that are shown on your main page changes, because that is constantly feeding back into your circuit or in your machine learning recommendations. So this is sort of the model that we have seen customers adapting it. And once again, all you do is you use node affinity here essentially to target it. So training, inference, or apps. The advantage of this case is because this is one cluster, so you really got to be careful because you are really making this one cluster as a single point of failure. So hopefully the cluster is big enough, or you can have replicated clusters across multiple regions to avoid that single point of failure. So you'd never want to do that otherwise. One of the key aspects that you want to understand on how do you scale the cluster? Well, by default, Kubernetes does not have the capability for the cluster to scale. So you need to install an additional component which will allow your cluster to scale. And why would you like the cluster to scale? Well, you would like the cluster to scale because your app is becoming popular and you want to run multiple number of pods, large number of pods to support that business workload. Now, in order for the containers to grow or the pods to grow, the cluster has to grow because essentially Kubernetes is a cluster-centric architecture. So for the cluster to grow, you need to have some mechanism. So either you use something called as cluster autoscaler, which is a component that needs to be installed, and it works based upon metrics, and it will grow the cluster or shrink the cluster, or a tool called as escalator. Let's understand the difference between the two. So cluster autoscaler is a tool that automatically adjusts the size of the Kubernetes workload of the cluster based upon the workload. By default, it is meant for burstable workloads because that's sort of what Kubernetes is. You get a request, and all of a sudden you're getting, instead of 1,000 requests, you're getting 15,000 requests, and it's a burstable workload. The deployment will take care of it. The replica sets will massively grow, but then if there is no space in the cluster, that's where the cluster autoscaler will grow the cluster so that your more number of pods can run. Now, that is okay for burstable workloads, stateless workloads. But if you go on the other side, escalator, that is targeted towards batch or job-based workloads, and which is what is more suited for machine learning workloads. Why so? Because machine learning training typically is running for hours, sometimes days. You don't want the job to be terminated, if the cluster is running out of capacity or if it needs to move it around. So one of the big differences between the two is also how cluster autoscaler would aggressively move your pods around to make sure the cluster is optimally utilized. The whole idea is pods are ephemeral. So if you have multiple number of nodes and it utilizes some of the pods, some of the nodes are not being utilized, so it will aggressively terminate the pods on one node, move them to a different node, so that node then gets freed up and it will remove that node out of it. So it kind of keeps the cluster optimally utilized. But that is detrimental for your machine learning workloads because you don't want the job to be terminated. Particularly if it has been running for 8 hours, you have to kind of pretty much resume all over. So escalator on the other side, wait for the jobs to be completed. So that's sort of the big difference that you want to think about it. Of course, cluster autoscaler can scale up based upon metrics. So you say, hey, my CPU memory threshold or app-based metrics, you can do HPA or cluster autoscaler based upon app-based metrics as well. So it will scale your cluster accordingly. But on the escalator side, it will look at what jobs are pending, because it does not want your pods to sit empty, waiting to be scheduled. That, okay, for example, I need 4 GPUs and 4 GPUs are not available, so it would not sit idle. It will aggressively scale up your cluster because they want to make sure that your jobs are completed on time. Sort of a fundamental difference between the two over here. They both take over the desired knob of autoscaling group, because end of the day is the autoscaling group in AWS that got to scale up and down. And in the same cluster, for example, we looked at pattern 2B, where we had training, inference, and say apps running in the same cluster. You could very easily say the training and the inference are going to use escalator, while the apps is going to use a cluster autoscaler. And that's sort of the configuration that we see customers using as well. Now, if you think about, we got the part about how do we set up clusters. Now, if we're using Kubernetes, then you need containers. So today, the challenge with the containers is, customers need to understand how am I going to build a container? I need TensorFlow, or I need a certain version of Python, or I need to abstract a certain CUDA driver, or I need to make sure the framework that I'm using is optimized for the cloud, or is it gonna run efficiently for me? So there are multiple challenges, and then it takes days, sometimes weeks, to configure and tune your parameters on what the right framework is gonna be. So, and then there's a new version of TensorFlow or a new version of another framework comes up, then you have to rebuild those containers, manage those containers. And that's the problem that our customers were telling us is important to them. So we launched AWS deep learning containers. With the deep learning containers, these are basically predefined set of Docker images, and you can leverage those images. Those images have the popular frameworks that matter to you for training and for inference, and you can leverage them with Amazon ECS, which is our fully managed container services as well, or self-managed Kubernetes on EC2 as well. Now, it does not restrict you from using it on any cloud, but the frameworks that are in there are tuned for AWS. So they'll give you a higher performance optimizations on AWS cloud. The different kind of container images that are available to you is a wide variety. So you can, there are like 16 combinations possible. So you can possibly choose TensorFlow for inference, for GPU, for Python 3.6. There is a tag for that that's available. And the reason the GPU and the CPU are different is because we want to make sure the images are optimal size. These images are huge, actually. They're like in the range of 2+ gigabytes. So we want to make sure that the drivers, only the relevant drivers are involved. So I would recommend take a look at the deep learning containers and see how you can leverage them as the base image, then bundle your application code, which is your training or inference code, and then there it is. All the frameworks that you need for getting started are bundled in there.
So if you take this approach of using your existing deep learning containers, and you don't have to pay for network travel because it's already in the data center, is that right? Or
well,
it's already in the container registries.
So it depends, because the question is, if you take this approach of using the deep learning containers, do you have to pay for the network traffic? The containers are sitting in Amazon Elastic Container Registry at this point of time. We are thinking about pushing them to Docker Hub so that they're a lot more widely accessible as well. Now, if you are running cross-region, depending upon where you are running, they're available in different regions. But if you're running regions where you are pulling it in from, that would definitely be a cost. But as opposed to downloading a 2.5 gigabyte on your laptop versus in the cloud, the speed is going to be a lot more efficient. So that's sort of the thing that you have to think about it. And there are ways.
All of the container images are available in all regions.
Oh, all of these are available in all the regions. They absolutely are. Now, one of the ways that you can also do is, for Amazon EKS, for example, end of the day, these images need to be downloaded on the worker node or on the data plane. So what you can do is you can build custom armies for the data plane and have these images preloaded over there. So then you are saving the time of downloading the 2.5 gigabyte, which is a runtime hit to you possibly, or start caching these images over there. End of the day is nothing but Docker layers that are sitting on your file system. One of the things that we have optimized, particularly for these deep learning containers, is TensorFlow. A lot of workload on Amazon EKS is machine learning centric, and a lot of customers are using machine learning using Amazon EKS. And a lot of them actually use TensorFlow. Well, TensorFlow is a machine learning framework. I won't get into the details of what TensorFlow is, but essentially, if you look at it, if we take a stock TensorFlow, what we realize is in our internal benchmarks, we could scale up to 256 GPUs, but we were only getting 65% return in terms of how long will it take to train a model. With the optimized TensorFlow that we have available in these deep learning containers, we could gain up to 90+% efficiency with 256 GPUs. That means you can keep scaling the number of GPUs, and the efficiency, the optimization that I talked about on how quickly you can get a trained model back is a lot better with the AWS optimized TensorFlow. Now, this is something that we are looking to contribute upstream because we don't want this to be restricted only for AWS, but this could be available to anybody. Now, let's switch gears. So we talked about sort of how we lay out the Kubernetes cluster, what is it that needs to be done from the containers perspective, how do we leverage them on Kubernetes. So if you think about, in the machine learning, what all needs to be done? Well, you need to have a model, you need to understand where your storage is gonna be, you need to understand how you're gonna run analytics, you're gonna understand what frameworks you're gonna use. All of those you need to think about it. And then depending upon whether you're running it in the laptop or training rig or cloud, each of those could differ. So that's sort of the challenge that the data scientists face. And particularly from a data scientist perspective, if I am coming on Kubernetes, I don't understand Kubernetes, but all I understand is the Jupyter notebook. So just get me going on that part of it. So that's their thought process. And it should be independent for them. They are typically running Jupyter notebook locally on their machine, but when they get to the cloud, the transition for them should be quite seamless. So think about Kubernetes. Kubernetes provides a basic abstraction to you, but on top of that, depending upon where you're running on laptop or training or cloud, each of those choices could completely differ. What KubeFlow provides provides a layer on top of Kubernetes where it standardizes on what that would look like. So all it says is, hey, we're gonna give you an abstraction layer on top of Kubernetes, an easy way to do machine learning workload. So today, if you're running, say, Kubernetes on your desktop and you install KubeFlow on top of that, it provides you a set of components. What that means is, if you're running Kubernetes on the cloud, then you will have the same set of components in the cloud. So the whole concept of about portability, whether you're running in the cloud, on-prem, or anywhere else, that is still applicable. And that's sort of the value of KubeFlow here. Now, what are the components in KubeFlow? Well, the main one is Jupyter Notebook, if you think about it, because that's exactly how data scientists like to start. So it comes in with Jupyter Notebook. It also comes with a TensorFlow controller, or TensorFlow operator. So essentially, it provides you a version of TensorFlow that is already baked in and installed as part of your Kubernetes cluster. There are other framework operators. There is Argo for CI/CD, for building a machine learning pipeline. And the most important part is how it gives you the wiring to make it work on Kubernetes. You have Kubernetes, you install KubeFlow, you have your TensorFlow, Jupyter Notebook, all of that baked in, and that's it. That's all you care about. That gives you a getting started experience for machine learning on Kubernetes. So how do we get started with KubeFlow? I'm talking about Amazon EKS here, particularly. So, well, you need to get KubeFlow. That's available on the releases page. So 0.6.1, I believe, was released 3 days ago. That's their latest release. They're working on 0.6.2 today. But the question that it's gonna ask is, hey, do you have a cluster or you don't have a cluster? If you have a cluster, then that's the easy route. But the interesting route is where you don't have a cluster. So in that case, it says you don't have a cluster. So you need to do a one-time initialization of the KubeFlow anyway. Then you need to set up AWS resources because you don't have a cluster. That means I need to create a cluster for you. So then it's got to define, okay, what instance types, what IAM roles, how big a node group that you want. It'll define all of those resources and it generate those resources. I mean, in terms of configuration file, then you have the ability to kind of start tweaking them. And then you say, now go ahead, apply the cluster, apply the platform, and this will create an EKS cluster for you. Then you get into the KubeFlow side of it. So you say, okay, now fine, I got my EKS cluster. Now create my KubeFlow resources, which are basically the Jupyter Notebook, TensorFlow operator, and everything that I talked about. Once again, you have the capability over there to say, I don't want the HTTP ingress controller. I want to use HTTPS instead. What kind of security do you want? Or I want to integrate with AWS Cognito for my OIDC-based authentication. So you can start tweaking those parameters over there. And then you say, okay, go ahead now generate the KubeFlow component as well. Well, if you have a cluster, then you just init KubeFlow, and then you say, go ahead, set up all the KubeFlow packages. Okay? So that's sort of the flow that typically what we work with. Let me get into the demo part of it here now. I'm gonna show you some of the stuff over here. Okay, so what I have here is I have a pre-created cluster for me, and in that pre-created cluster, I have the files over here. So if I go to say AWS config, I can say open cluster config.yaml. And this is sort of very similar to my eksctl config, where I'm saying, here's a GPU node group, here's the instance type, here are the availability zones, I want 2 nodes here, and here is my key name here, okay? So that's how I'm gonna generate my cluster over here. And I can also open cluster features, for example. And this is basically saying, okay, do you want your API server endpoint to be publicly accessible or not? And you can start tweaking that over here. As I talked about, the integration of control plane and data logging to CloudWatch, that all can be configured and tweaked over here. You don't have to do that right now. This can be enabled later as well. But the whole ability that you can do that from KubeFlow itself, we want to provide a seamless experience to the customers. So now what I have is, actually I'm going to go to my wiki here. So if I go here, this is my AWS console. And if I look at EKS, so here it shows KubeFlow AWS cluster that is created for me. And this cluster was created about a week ago. And what I can do is, I'm actually gonna I'm gonna share a repo with you where all the code is available. So if I go to the wiki here, okay, so what I wanna show you here is, so if I say kubectl config get context, okay, it's going to show me all the contexts that are available. So I have a few clusters, EKS clusters running over here. So now KubeFlow is my cluster right now. That's the one that is being pointed to. So I can say, show me the number of GPUs in that cluster. So it's going to say it's 32 CPU and 4 GPU cluster. So total it has 64 CPUs and 8 GPUs. That's a pretty decent cluster to run my nodes. Although our customers run a lot more like P3, DN, 24x large kind of an instance they will run, and they will run lots and lots of those to run their machine learning models, depending upon the scale, okay? So now what I wanna do is, I wanna show you a typical data scientist experience here. So I'm just gonna get ingress here. I'm gonna grab the ID for me, and I will say, run the thing here. This is my KubeFlow dashboard that is available to me. Now I'm gonna go to notebook. So as a data scientist, I will just say create a new server. So we'll say J4K. I'm just gonna increase the CPU to say 1 CPU. And then I'll say, go ahead, spawn my notebook here. So it's gonna create my notebook up in the cloud. There's nothing running on my local desktop here. So it just goes ahead and creates my notebook here. In the meanwhile, what I'm gonna do is I'm gonna grab the code from here. So this is my code here, okay? So I'm gonna grab it all the way down here. This is exactly how I built my container as well. So what I'm showing you is, as a data scientist, you can keep fiddling with your Python code. When the Python code is ready, then you can say, now go ahead and take this code and bundle it into a container. So let's see if our thing is ready. Yeah, okay, this is ready. So I'm gonna connect to the notebook here. Oh, what happened? I think it's still creating it. Hello. Sometimes it reports the status and the notebook is not ready. Oh, there we go. Now it's coming up. Yeah. Yeah. Well, the idea here is once the notebook comes up, then you just drop the code over there and then they go run it. And as a data scientist, you can start editing your Python code, and that will generate your model. So until, as a data scientist, you are satisfied, once you're good, then you say, okay, this code is ready, check it into the GitHub repo. Then the other team, who's gonna convert this into a container can actually do the job for converting into a container here. So let's refresh it one more time. Yeah, I don't know what's going on here. So that's like a typical data scientist experience. Now, I think we have just about 5 more minutes here. So I want to skip the Jupyter Notebook concept here. One of the things that we can, so then the whole workflow is essentially your code is now working in sort of the Jupyter Notebook kind of a flow. Now you can take that code, convert it into a container, run the training in the cloud, and once you have run the training, then your model is stored in the cloud. Now you can do inference. So for inference, basically what I'm doing is I'm using MNIST dataset. MNIST is a standard dataset that is available to anybody. And it is basically, well, I'm using Fashion MNIST dataset. And Fashion MNIST is a dataset that is generated by Zalando. And it is basically a bunch of images from their online catalog. And it is a bunch of fashion images, okay? So what I'm gonna do is I am gonna go here, actually here, and here, and here. Oh, here actually, not this wiki here. So I have the training module or the inference module already running, inference pod already running in the cloud. So all I'm gonna do is I'm gonna show you, well, first of all, let me make sure I do the port forwarding correctly here. So this port forwarding will allow me to make sure I can actually access the inference endpoint on my local machine. And now I am going to just invoke the inference module here. So all I'm saying is endpoint HTTP localhost 8500, and this is where my model is. It's a little blurry image because it's a 28 by 28 pixel, but if you see here, what it's doing is it says the model thought this was a shirt class 6, and it was actually a shirt class 6. So it just pops a model, kind of look like a shirt in a 28 by 28 pixel.
It's like Pikachu.
Yeah, Pikachu shirt maybe. Now if you run this thing again, then the idea is it picks up a random image from the model, and then it says, well, this looks like a purse or a bag maybe. Oh, it's a bag class 8. So it kind of returns that thing. Now in this case, I'm picking a sample data from the test data itself, but in your ideal world, your test data is different, your input data is different, and your real world data is completely different. And that's where you test the validation of the thing. Couple of points that I want to quickly highlight here as well is customers end up doing, single node training may not be enough. So a lot of customers end up doing distributed node training, where they have these multiple nodes that are running in your cluster, and in those clusters is where you're spreading it out. So Horoward is a framework by Uber. So a lot of the customers actually use Horoward for doing distributed node training. And we can just talk about this aspect like for the next 45 minutes, but I just want to introduce the concept to you here. The other part we were talking also about is high performance file system. So FSX for Lustre is a file system that we announced at reInvent last year. It basically gives you a very high performance file system, front-ending Amazon S3. So your data could be sitting in Amazon S3, but this is a front end to that. And the way Kubernetes works is, anytime you're talking to a storage system, you really need a CSI driver or a container storage interface. So what we did is we wrote a CSI driver, which is out in the open source, that allows you to connect with FSX for Lustre from your Kubernetes pods, essentially. So that's what the distributed node training is. This is a quick summary of where we see what are the advantages of running KubeFlow on AWS. And this is barely a start at this point of time. All the docs are available on kubeflow.org/docs/AWS. This is a project that I'm actively working on with the containers team these days. So if you have any feedback, if there are feature gaps, product gaps, I would love to hear from you. Something that we also did for our customers is, customers often ask us, what are the best way by which I can optimize my Kubernetes cluster running on AWS? So we published a toolkit by which you can take that toolkit, run it on your Kubernetes cluster, and it will tell you, how does your Kubernetes cluster look like? And it kind of gives you recommendations as well on how you should tune your Kubernetes cluster. But this one shows basically how you can tune up to, like if you're running multiple nodes here. So in this case, for example, we were able to scale quite linearly for up to 160 GPUs running on Kubernetes. So if you're running like a 160 GPU node cluster, your thing is gonna scale on Amazon EKS. So we're really talking about that Amazon scale over here. I think I'm gonna pass it here. So the key repo that I want you to leave with is here. Hello. So this is the main repo that I would like you to leave with. Now this is where all the code, all the sample. So if you want to do distributed node training, if you want to do single node training using TensorFlow and Keras, MXNet and Keras, or distributed node training here with ImageNet data. If you want to run a Jupyter notebook on Amazon EKS, all the code is available over here, and we are actively maintaining this workspace. So if you have any questions, feel free to file an issue or send a pull request. I'm going to be here the rest of the day, so we can do more discussions. Thank you. Sorry, let's talk.